In this segment, we will find the exact solution of a first order ordinary differential equation. So let's go and take this example here. We are asked to solve this first order ordinary differential equation. This is the initial condition of that ordinary differential equation, and we're supposed to find y at 3. The solve is of this form. So let's go and see that how can we solve this particular problem. So the solution will be the homogeneous part plus the particular part. So let's concentrate on the homogeneous part. So in order to find out the homogeneous part of the solution, what we're going to do is we're going to say that, hey, let's define our differential operator to be d by dx like this. Then this differential equation can be written like this. And then we get d plus 0.4 being plus 0.4 being operated on y. And the reason why we wrote it like this because this then directly gives us the characteristic equation, which will be m plus 0.4 equal to 0. That'll give us m is equal to minus 0.4, and that'll give us the homogeneous part of the solution is k e to the power minus e to the power mx, which will be minus 0.4x. So that is the homogeneous part of the solution. Now let's go and find the particular part. The particular part will be of the form a e to the power minus x. Why is that so? Because if you look at the right hand side, the forcing function of this differential equation, it is 3 e to the power minus x. So all its derivatives and its form is of the form of e to the power minus x, because the derivative of e to the power minus x is minus e to the power minus x. The derivative of that is plus e to the power minus x. So you're always getting the same form of e to the power minus x. So that can be all bundled into just one single expression of a e to the power minus x. How do we go about finding what a is now? We substitute it back into our differential equation, the particular part of the solution which we just have given the form of, and let's see what happens. So we take d by dx of e to the power minus x here. So derivative of this is minus a e to the power minus x, and you get this quantity right here, and this will be 0.6 a e to the power minus x, and this here gives you a equal to minus 5. What this means is that the particular part of the solution is nothing but minus 5 e to the power minus x. So you have found the particular part of the solution. So let's go and now add the homogeneous part and the particular part to find out what the complete solution is. So the complete solution will be the homogeneous part plus the particular part. The homogeneous part is k e to the power minus 0.4x. The particular part is 5 minus 5 e to the power minus x. So how do we find k? We find k by knowing that the initial condition is given as 5. So substituting the value of x equal to 0 into this gives us 5 equal to k e to the power minus this quantity minus 5 e to the power minus 0 here, and that's k minus 5. That gives us k is equal to 10. So what that means is that the whole solution will be 10 e to the power minus 0.4x minus 5 e to the power minus 6. So that is the solution to the ordinary differential equation. But we are asked to find out what the value of y at 3 is, which will be this quantity right here. And this number here turns out to be 2.7630. So that is the exact value of y sub 3 up to 5 significant digits based on the exact solution. And that is the end of this segment.